Here I want to look at finding the integral using the change of variable method, often known as the U-Substitution method. Here we want to integrate the square root of 2x minus 1 dx. And the first thing I notice is that this integral kind of looks like the chain rule, but with integrals instead of derivatives. And that's exactly what makes it perfect for U-substitution. The fact that we have a function inside of another function. So to begin, I want to identify something as being u. And what I want u to be is the inside function, that 2x minus 1. Then we'll find the differential of u, which will just be 2 dx. All of this is going to help me to rewrite the integral and make it a lot easier to find. For instance, since u is that 2x minus 1, I'm going to plug u in underneath the square root. Also, I have to substitute something for dx, and that's where this comes into play. Because I have this equation du is equal to 2 times dx, that means that dx is equal to 1/2 of du. And that's what I'm going to substitute in here, 1/2 of du. Now, we do have the constant multiple rule for integrals, which says if I'm multiplying by this constant, this 1/2, I can actually pull it out of the integral and just take the integral of the square root of u du, which is much easier to do. I know how to take the integral of the square root. The integral of the square root of u is 2/3 u to the 3/2. Now, all I have to do is resubstitute everything in, simplify this all out, and we're done. So 1/2 of 2/3 is going to be 1/3. And we have u to the 3/2. But u was 2x minus 1. And we finish this off with a plus c because we're talking about the indefinite integral. And here is the entire integral. Here we have another one that looks pretty frightening. The integral of e to the tangent of 2x times the secant squared of 2x dx. We have a lot of things that are going on in here, but one thing that we do notice is that I've got a function inside of a function. That's what's going to make this good for U-substitution. Now there's a couple instances of functions inside of functions. I got tangent inside of e, but I also got 2x inside of tangent, and secant inside of a squared. All sorts of things are going on here. And we may have to try all of them before we come across one that's going to work. But because we have functions inside of functions, this might make U-substitution a good method. So first, I'm going to identify my u as that tangent of 2x. Then the differential of u, the derivative of tangent, is secant squared. And the derivative of 2x is 2 dx. That's real nice because I see that secant squared 2x also in my integral. So we're going to start plugging things in. I have the integral of e, and that tangent of 2x, well, I said that that was my u. Then we have secant squared of 2x dx, which is really, really close to this. So I'll just rearrange it and find out what secant squared of 2x dx is. To do that, I have to divide off this 2. So 1/2 of du. So we'll have e to the u times 1/2 du. Again, I have that constant of 1/2 that I'm going to pull out in front of my integral. And then take the integral of u du. Which is easy. The integral of u, e to the u, is e to the u. So this will be 1/2 times e to the u. Once the integral is taken, now it's just a matter of writing it in terms of x. So we'll have 1/2 e to the u being tangent of 2x. That's it. So we'll finish it off with a plus c because it's an indefinite integral. Here's another fairly gnarly looking integral. We have the integral of negative 4x over 1 minus 2x squared dx. One thing that is noticeable right off the bat is that it looks like we have a function inside of a function. So that's what I'm going to focus on and think that maybe U-substitution might help us out here. So I'm going to let 1 minus the 2x squared be my u. Then its differential would be negative 4x dx, which is helpful because I see both of those in my integral. So let's start substituting. First, we have the integral, and in my denominator, that is where I have my u that's getting squared. After that, I still have negative 4 and dx. 4 dx. Luckily, it all matches up. I don't need to rearrange my du. That is du. So my numerator will just be 1. In this integral, then, I don't have to worry about a constant. I can just look at this as finding the integral of u to the negative 2 du, which means I'll have to increase the power by 1 to negative 1, and then divide by that. So we'll have negative 1 u to the negative 1. Finish it off by writing it in terms of x. Negative 1 over u, which is 1 minus 2x squared. Finish off with a plus constant because it's an indefinite integral. And we're done. Now we have the integral of x times the square root of 2x minus 1 dx. Looks very similar to the first one in this video, but there's this extra factor out in front, x. However, we still do have a function inside of a function, which makes me think that this will be good for U-substitution. So I'm going to identify my u as being the inside function, this 2x minus 1, making du equal to 2 dx. When I try to substitute everything in, I do have this square root that is going to be my u. From the dx, I do see that I can get that from here. The dx is equal to 1/2 of du. So I can plug that in for my dx. 1/2 du. The problem is I still have this x to deal with. I need to have an expression in terms of u that I can replace for x. And that's going to come from here. Since I know that u is equal to 2x minus 1, that means that x would have to be u plus 1 divided by 2. And that's what I'll have to substitute in right here, u plus 1 over 2 for that x. Now it looks like what we've done here is just made this thing a lot uglier and a lot worse. But in actuality, we really didn't. What we should do now to see that is to simplify it a little bit. For instance, I have this fraction of u plus 1 over 2. I can make a second fraction out of the next two factors, where 2 is my denominator, and I'll have square root of u in the numerator, or u to the 1/2. I will continue simplifying this by combining these two fractions into 1, multiplying the denominators give me 4. In the numerators, I'm going to have to distribute the u to the 1/2 into u plus 1. That'll give me u to the 3/2 plus u to the 1/2. Still have du on the outside. Since we're dividing by 4, that's the same as multiplying by 1/4. I'm going to pull that 1/4 out of the integral and be left with u to the 3/2 plus u to the 1/2 du. And this is an integral that's much easier to find. So, integrating u to the 3/2, I'd have to increase the power by 1 to 5/2, and then divide by 5/2. That give me 2/5. The integral of u to the 1/2 would be 2/3, u to the 3/2. Our last step is to simplify this expression and write it in terms of x. So I'll distribute the 1/4 inside. 2/20 is 1/10. U to the 5/2, my u being 2x minus 1. And then I'll have 1/4 times 2/3, 2/12, which is 1/6 times 2x minus 1 to the 3/2. And since this is an indefinite integral, I'll put my constant of integration on the end. And there we go. All right, if you need one more example, here's another one. The integral of x plus 1 times the square root of 2 minus x dx. Again, I see that we have a function inside of a function right here. So that tells me that U-substitution might be a good method. And I'm going to let my u be 2 minus x. That means my differential of u is going to be negative 1 dx. When I substitute all that stuff in, let's see what we have. Over here I have my square root, and the 2 minus x, that was u. dx, we can get that from right here. dx would equal negative 1 times du. So, negative 1 times du. Now, I still need to substitute for this x plus 1. And from my first equation, u equals 2 minus x, I can solve that and find out that x is going to equal 2 minus u. So I can plug that in there just for the x. And that'd be 2 minus u. I'd still have to add 1. All right, it looks messy right now, but we'll clean it up and see if it does become a little bit easier. When I simplify what's in the parentheses here, we'll have 3 minus u. The square root of u times negative 1, that would be negative u to the 1/2 du. Continuing simplifying all of this, we'll have to distribute that negative u to the 1/2, giving me negative 3u to the 1/2 plus u to the 3/2 du. And now we're ready to integrate. So let's do it. Negative 3u to the 1/2. That means I would have to increase the power by 1 to 3/2. And then take 3 and divide it by 3/2. Plus u to the 5/2 and divide by 5/2. That leaves me 2/5. Or, simplifying a little bit, it looks like that would make negative 2 u to the 3/2 plus 2/5 u to the 5/2. And our last step is to substitute in for x. So negative 2 times 2 minus x to the 3/2 plus 2/5 times 2 minus x to the 5/2. And don't forget your plus c because it's an indefinite integral.